Hello Finxters. Today we'll take a look at how a depth-first search algorithm works. Here we have a simple graph made of several vertices. Our beginning vertex will be vertex number 5, and we'll look for vertex number 6. So as you can see, our graph is connected with our vertices are connected with several edges. And what is specific about depth-first search algorithm? It will not necessarily follow the exact edges that would give us a shortest possible path connecting our starting and our ending vertex. So to begin with, we'll start with vertex number 5 and analyze what are his neighboring vertices or neighboring edges. So in our case, we have the neighboring vertex numbered 3, and there is also a vertex numbered 0. The algorithm works by first selecting one of his neighbors. So in our case, it will start with the vertex number 3. Now that it has explored vertex number 3, it will progress downwards. So contrary to, for instance, breadth-first search algorithm, the depth-first search algorithm tries to go the fastest possible. Tries to find the fastest possible way to reach the ending vertex. So it means it will not go by exploring all of its neighbors in the first round, but it will try to go further and further the fastest it possibly can. So in this way, by selecting vertex number 3, it will progress to its only unvisited neighbor, and this is vertex 4. From vertex 4, it will also progress to vertex 0, and here we have a vertex with two neighbors, and these are vertex 1 and vertex 2. By following its first neighbor, you cannot see from this graph which one is the first, but when you take a look at the code, at the example in the article, you will see that the algorithm traverses the list of elements, and that the vertex number 1 is the first one defined. So actually the edge connecting vertex 0 and vertex 1 is defined first, and then we have a definition of the edge between vertex 0 and vertex 2. So this is why we will first visit the vertex 1. By visiting vertex 1, we can see that it has no other possible neighbors to continue the depth first search. So it will backtrack to vertex 0, and from there on it will continue and select the vertex number 2. It will explore it and conclude that there is another vertex which is unvisited, and this is our vertex number 6. By exploring vertex number 6 and by following, actually by testing our trivial condition in the code, we will see that by exploring vertex number 6, we have actually found the entity we are looking for, and now we are able to establish a complete path which led us to the vertex number 6. So in our case, we will go backwards. This backtracking actually corresponds to returning from recursively called functions, and in our concrete example, this will look like going from 6. You can see here on the right side the output of the function, which you can run yourself. And by following this search path in reverse, we actually form our search path in code. It is reversed from the beginning to the end, and it states that by starting at vertex 5, we will go to 3, 4, 0, 2, and 6. As I mentioned in the beginning, you can see that the search path this algorithm produced is not necessarily the shortest one. Actually, it's the longest one here, because it could have also been a path from 5 to 0 to 2 to 6, and then it would be the shortest one. But here we have our algorithm running like this. So it still did produce a path connecting both of our vertices, but it's not the shortest one. You can play with it in the example from the article. You can just copy and paste it. Just don't forget to import the graph module from the previous exercise, which was on breadth first search algorithm. And actually, that article was a double one. It first talked about graph class and graph abstract type, and after that it focused on the breadth first search algorithm. So here we have our example. I hope it was useful to you, and also I hope you'll have some fun with the article, with experimenting with the algorithm. And until the next time, have a nice time and bye bye.